Hello everyone, welcome to Introduction to Artificial Intelligence System. Today we're gonna learn basics of linear algebra. As many of you are already familiar with, a linear equation is an equation that has a form of ax is equal to b. And if there are several multiple linear equations, we call this as a set of linear equations. So for example, let's take an example of set of linear equations that has two equations with two unknowns. So for example, in this set of linear equation, we have two unknown variables like x1 and x2, and we have two equations. And we know how to solve these linear equations, right? By multiplying the two to the second equation, we can sum the entire two equations. We first remove the x1 variables and then get a x2 is equal to 5, and then by putting this x2 into the first equation, we can solve x1 as well. And another way to express this set of linear equation is using a vector form. So in this case, we can just simply take the coefficients of these linear equations. So by taking the coefficients of these unknown variables, you can write the A matrix, and by writing the unknown variables as a vector x, and by writing the constant variables into vector b, we can rewrite the set of linear equations in a vector form with ax is equal to b. And in this vector form, we can simply also solve the solutions by multiplying the inverse of a into both left-hand side and also right-hand side. We can solve x is equal to a inverse times b. And in more general form of systems of linear equations, let's consider a system of linear equations with n variables and also m equations. In that case, we can also rewrite this set of linear equations in a matrix form with y is equal to m by 1 vectors and a is equal to n by n matrix, and x is equal to n by n matrix, n by n vectors with unknown variables. And when we think about the basics of matrix, we can simply rewrite the matrix in terms of its columns, or also called column vector. So for example, let's say if A matrix is equal to A11, A12, blah blah, A1n, A21, and AM1, then its elements can be divided into its column vectors. So let's say this one should be the first A1 column vector, and this one should be considered as the second A2 column vectors. And similarly, these A matrix can also be interpreted as in terms of its rows or its row vectors. So firstly, in this case, this vector could be the first row vector, and this could be the second row vector. And here, as a convention, we're gonna write the one vector as in the form of column vector. So to do that, we're gonna write the row vector as the transpose of the B1 vector. So this could be written as a B1 transpose vector, and this could be written as a B2 transpose vector. Yeah, so far we have learned the basics of linear equations, and let's implement these linear equations in Python to solve the set of linear equations. So for given these set of linear equations, we first need to rewrite this form in a matrix form, right? Ax equal to b. So here A matrix should be the 4, minus 5, minus 2, 3, and X matrix should be the x1, x2 variable, and B matrix should be a minus 13 and 9. So by taking this A, X, and B matrix, let's implement this matrix into Python code. So to do that, we first need to import a NumPy library as NP for a short code. And then let's define A matrix and B matrix by using NumPy array function. So here, to write the matrix, we first need to use bracket to represent the first row in one bracket and write the second row in this bracket. And then by using additional bracket, we need to combine these two as a matrix. So here, by doing so, we were able to define 2 by 2 matrix. And similarly, for the B matrix, we only have one component in the first row, so we can see the one element of minus 13 is written in the first bracket. And by writing the second row and by combining these into a matrix, by combining these, we were also able to define 2 by 1 matrix, 2 by 1 NumPy array. And then here, to solve x from here, we can simply obtain this x is equal to A inverse times B, right? By multiplying A inverse into both sides, we can obtain this. So let's implement this to Python code. So here for this, we need to use a NumPy linear algebra function, and here by taking inverse A function, we can calculate A inverse, and here by using dot B, you can calculate x, which is equal to 3, 5. So here you were able to obtain the solution of this set of linear equations. In other way, we can also from this step we can also use another way by using NumPy as matrix function. This as matrix function converts the NumPy array into a matrix form. So here we don't need to calculate this step. We can just simply calculate A inverse multiply B, which is equal to the same result. So here, from now, let's learn several basic matrix operations. So to do that, firstly, let's learn vector products. We know from linear algebra class, we have learned two types of vector products. The first one is called dot products, or called inner product. And the second one is cross product. And here we're gonna only learn the inner product. So inner product of two vectors x and y can be calculated can be expressed as x dot y or x transpose y or y transpose x. And this can be calculated by multiplying its element in a element wise. And secondly, we're gonna learn the matrix products by expanding the vector products. So the matrix vector products between matrix A and X can be expressed as a linear combination of the columns of A with coefficients given by X, which means by multiplying by calculating products between matrix A and X, matrix AX can be written as A1 x1 plus vector A2 x2 plus a3 x3 plus blah blah blah. And we know that x1 and x2, x3, and xn are just elements of the x vectors. So these are just a scalar number, right? So and an vectors are all column vectors of these A matrix. So this means we can simply interpret the matrix products as a linear combination of each column vectors. So by knowing the several matrix operations, let's also implement matrix operations in Python code. So firstly, let's calculate inner product using Python. So for this, let's first define the matrix. Let's first define two vectors of x and y, which is equal to 2 and 3. And here, by calculating x transpose y, you can calculate the inner product between x and y, which is equal to 5. And in other way, you can also use as matrix function. So by defining this NumPy array into matrix, you can calculate x transpose y, which is equal to 5. And the second example is matrix vector product. So to do that, you first define A matrix 1, 2, 3, 4, and B vector as 5, 6. And by defining these A and B as matrix, and by calculating A cross B, you can also get a result. Yeah, and now let's learn one of the special form of matrix, which is symmetric matrix. A symmetric matrix has several interesting phenomena, so you guys should be familiar with this. By definition, we call a matrix with a square size as a symmetric matrix if its transpose is equal to the matrix itself. So for example, if A matrix is equal to A, B, C, D 2 by 2 matrix, in order to be a symmetric matrix, the off-diagonal components should be a mirror symmetric. So that means the matrix should be like this. And you can also construct a symmetric matrix for given any matrix by multiplying the transpose of matrix itself into the matrix itself. From now on, I'm going to introduce a very important concept of norms, or also called strength or distance in linear space. So you can simply just think a norms of a vector as a length or size of the vector. By definition, a vector norm can be any function that satisfies the following three conditions. The first one is that as it measures strength or distance or length, it should be always greater than or equal to 0. And if norm is equal to 0, that means x is equal to 0. And the second condition is that when we multiply a into the norm, then it should be equal to fx times the absolute value of a for any a in real space. And the third condition is x plus y should be always smaller or equal to fx plus fy. And these are the conditions to be a vector norm. And so if any function satisfies these functions, then that can be a vector norm. And actually, there are two types of very important norm, which the first one is L2 norm and L1 norm. And I guess you guys are already familiar with this L2 norm, which can be represented as mathematically like this. So L2 norm is just simply you can calculate the square of each element and then take the square root. So in geometrical interpretation, uh, let's take an example of one point here. So as I mentioned, norm is just strength or distance. So the norm can be interpreted as the distance from the origin. And the easiest way we are saying the length is just by taking the square of each direction, and then by taking the square root, we can calculate the distance, right? And actually this one is just L2 norm. And the other way to measure the size or norms from the point from the origin is just measuring the absolute value. So here in this case, we are going to 3 steps in the x direction, and we need to go the 4 steps in the y direction. So this case, like taking each steps like this could be the L1 norm. So L1 norm can be like 7 in this case. So anyway, the x measures the length of a vector from origin. So you need to remember these very important two types of norm. So for this, let's also implement these norms in Python. Luckily, we already have a very important function, which is numpy.linearalgebra.norm. So by just taking L2 norm here too, you can simply calculate you can simply get a result L2 norm. And by taking this 1, you can also get a L1 norm. Yeah, and now, from now, we're gonna learn the very important concept of orthogonality and angle between vectors. Actually, when we have learned the linear algebra, we have learned two important angle between the two vectors. The first one is the right angle, and the second one is the parallel. Yes, so based on this formulation, let's first define a half space. Half space can be interpreted as a collection of x vectors that satisfy the following conditions. And this concept comes in importance later on when we learn the concept of classification. So you guys should be keep in mind the concept of half space. So as we already learned in the previous slide, the inner product is just simply the two norms multiplied by the cosine zeta, where the zeta is the angle between two vectors. And in order to be these values should be less than or equal to 0, we know that the cosine zeta should be negative or less than 0 or equal to 0, because we know that norms always are larger than or equal to 0. So this should be negative. So when we think about the y vector, and let's think about the cosine zeta, then we know that the cosine zeta is negative when the zeta is larger than 90 degrees and less than 270 degrees. So zeta should be in this region, and that means the x vector should be at least larger than 90 degrees and less than 270 degrees. So that means the x vector should be located in this region. So we call this as a half space. Yeah, so in previously we have learned the matrix multiplication. So by multiplying A into the vector x, we have learned the matrix operations. And actually, the interesting thing is that we can interpret this matrix multiplication as a matrix transformation. That means by multiplying x vectors into M matrix, we can get another result of a matrix vector y. So this can be interpreted as transforming vector x into y by multiplying M. So these can be interpreted as like this. So for a given linear transformation, you can um, write the linear transformation into a matrix, and also for a given matrix, you can interpret this as a linear transformation. So by inputting x, you can transform the x by multiplying m and getting y as an output. And among various transformation, we're going to learn a linear transformation. I guess we are already familiar with the terminology of linearity, right? So for when we talk about some function which is ax plus b, we call this we can plot this graph as some linear function. So the linear comes from the terminology from like this. And so when you talk about the linearity, two characteristics should be preserved. The first one is additivity, and the second one is scaling. So when we think about these two characteristics, we can clearly see that the additivity and scaling has been used in this form. So when we are talking about a linear transformation, this is also means a transformation from one vector to another vector, but this should satisfy the following two conditions of the additivity and scaling. So when some transformation that satisfies the following two conditions, we're gonna call it as a linear transformation. So let's take some examples of linear and nonlinear transformation. Of course, the constant function or fx is equal to kx, it should be a linear, while the x squared is not linear, is nonlinear, because this function does not satisfy the following two conditions. And similarly, for the function that use derivative or integral is also kind of one of the linear functions, and sine x or x plus c does not satisfy the following conditions, so we call these functions as nonlinear transformation. And the reason why we are learning linear transformation is that it's very simple and it's very basics. So assuming that we know some two bases and eigenvectors, and assuming that we know the linear transformation of these bases, in that case, for any by definition, for any vectors, we can describe any vectors using these two bases with a linear combination, right? This is the definition of basis. So in that case, yeah, and from now on, let's take couple of examples of matrix transformation. The first example is rotation. Is a rotation operation linear? And it's simple answer is yes. So the question is then, how can we obtain the linear transformation to rotate the set? rotate one vector to another vector. So let's say in this case, if you want to rotate the vectors with an angle theta, the rotation matrix should be in the form of should be the function of theta, right? So here, so the matrix can be written as some rotation vector as a function of theta, and this transformation matrix then should be rewrite as y is equal to r theta x. Yeah. So the remaining problem is then how can you find a matrix that rotate one vector to another vector with an angle of theta? And luckily, in previous slides, we have learned that the rotation matrix is kind of a linear transformation, which means these R zeta linear transformations satisfy two conditions of additivity is equal to tx plus y, and also scaling properties. Tax is equal to atx. And these two properties ensure that the rotation matrix, we can simply obtain rotation matrix by using two bases. So let's start with the very simple basis of 1, 0. So we know that if the 1, 0 vector will be transformed to cosine theta, comma sine theta, right? In this case, by rotating this vector, the x component of this vector would be cosine theta, and the y component of this vector would be sine theta. So the vector would be transformed to like this. So by putting these results into this equation, we can obtain this following equation. And also similarly, we can also transform these another basis of 1, 0 vector. By rotating this, we're gonna have the minus sine theta and cosine theta vector, right? So by rotating this vector with an angle of theta, then the transformed vector would be like this. So from that, we're gonna have the second equation. And finally, by leveraging the linearity of this transformation matrix, then we can combine these two matrices, right? So when we put 1, 0 vector, then the transformed vector would be cosine theta and sine theta. And when we put 0, 1 as an input vector, then the output vector would be like minus sine theta and cosine theta. That means the R0 theta would be, and this one is actually an identity matrix for 2 by 2 matrix. So R theta would be like the cosine theta minus sine theta, cosine theta. So this one is the very simple way to obtain the rotation matrix. So note that we have find a matrix form by using two basis vector by leveraging the linear transform properties. So the second example of matrix transformation is projection. And projection operation is also one of the linear transformations, so we can use the same way when we used to calculate the rotation matrix. So here, let's say P as a projection matrix onto x-axis. Then in this graph, then we know that the original vector x projected onto x-axis would be changed to like x, which is equal to x1 and 0, because the x and y vectors share the common x1 values, and its y component would be changed to 0. So here, using the same way, we can use the two bases of 1, 0 and 0, 1. So when you project onto the 1, 0 vector that onto x-axis, then it will not change. It will not be changed, right? And if we project onto this 0, 1 vector, then it will be projected onto an original point, so 0, 0. So by combining these two bases, we can construct these relations. So here we can obtain the projection matrix like this one. And the final example of a matrix transformation is scalar multiplication. We know that scalar multiplication is just stretching or compressing the vectors while keeping the direction. So it's like making a parallel vectors by stretching or compressing. So by knowing this relation, we can use two bases. We can use these two bases, and by constructing these vectors, we can construct scalar multiplication vectors. As we can clearly see that still this can be also represented by a matrix, which means this can be represented as a matrix transformation. Yeah, and finally, let me combine these into multiple transformation. So let's say we have two steps of transformation. Which one? The first one is T1, which transform one of matrix M1, and second one is transform 2, and which can be represented as matrix M2. And let's say if the transformation of T is just operating transformation first, and then followed by transformation 2. That means, let's say we have original vectors of x, then this then be transformed to y vector by operating t1, and then this one is then also changed to g vector by operating t2. So let me rewrite this step by step. So here, from the first step, we can see that we can rewrite this as y vector is equal to m1 times x, right? And from the second step, g vector is also equal to m2y. And here we know that y2 is equal to m1x. So by rewriting this, g vector is equal to m2 m1x. So these m2 multiplied by m1 can be rewritten as m. So here, in that case, the transformation of t operating t would be rewritten as m2 by m1. So here, you should be noted that these vectors, these operations should be written from the right side. So which means if you want to take T1 first, then the matrix M1 should be written in the right side. Yeah, so far we have learned the basics of matrix transformations. So the core idea is that the multiplication between a matrix and vector can be represented as a matrix transformation. Matrix transformation. So by keeping in mind this concept, we're gonna learn eigenvalue and eigenvector. I understand you guys already know the how to solve eigenvalue and eigenvector problem, but here you should know that the physical or mathematical meaning of eigenvalue and eigenvectors. So when we know that the multiplication between matrix and vector can be interpreted as matrix transformation, then we can interpret this one as a matrix transformation of vector v. And here, this one, the lambda is scalar value, which means lambda v is equal to lambda v is parallel to original vector v itself. So this means the matrix transformation, and this means the scalar multiplication of vector itself. So that means we can say the lambda v is equal to stretched or a compressed vector while keeping the same direction with vector v itself. And AV can be represented as some linearly transformed vector because we interpret this as a matrix transformation. So generally, it rotates or stretches. So by rotating, its direction can be changed. But as you can see here, they are the same. So that means when you transform one vector, but its direction is preserved. So that's why we call this as a eigenvector, a unique vector and very special vector. So in general, most of other vectors would be changed like this. But for special eigenvectors, its linear transformation would be changed while keeping its original direction. So that's the physical or mathematical meaning of eigenvalue and eigenvector. For your information, let me briefly recheck how to compute eigenvalue and eigenvectors. I guess you guys should know that how to solve eigenvalue and eigenvector problem. And by letting this equation, we need to solve this equation. So for that, we firstly need to calculate eigenvalue that satisfy these deterministic equations. And then by calculating its eigenvalues, we should find the eigenvector that satisfy these equations. So here we need to find eigenvectors. So these are the two steps of computing eigenvalue and eigenvector. You guys should know that how to compute this eigenvalue and eigenvector. And as we are dealing with the basics of artificial intelligence, then we're gonna implement calculating eigenvalue and eigenvector in Python code. So here, let's first define the A matrix. So here, by using np.array function, we first defined the A matrix. Then, by using very simple function like np.linearalgebra.eigena, then we can have the eigenvalue and eigenvector respectively. So here, D is just simply eigenvalue and V's are eigenvectors. So you can see that when you print out this eigenvalue and eigenvector, you can simply get a solution. Yeah, in the last part, we're gonna take a look into systems of linear equations, and there are three types of problems. So depending on the problem setting, we can divide the systems of linear equations into three types. The first one is well-determined linear systems where the number of variables is equal to the number of equations. So here we have two unknown variables, and also we have two linearly independent equations. So here equations can be also can be also regarded as constraints. So by plotting these two equations, we can find the one crossing point, which would be the exact solution, one and only exact solution of these systems of linear equations. And that's why we call this system as well-determined linear systems. And the second type is underdetermined linear systems, where the number of variables is larger than the number of equations. So here we have two unknown variables, but we only have one constraint. So by plotting this equation, we can find the solution where any points on this line could be the solution. So we can have many solutions. And finally, the third type is overdetermined linear systems, where the number of variables is smaller than the number of equations. So here we only have two variables, but there are three types of equations. So when we're plotting these equations, we cannot find one common point that satisfies the following three equations. So there will be no solutions. And let's see the set of linear systems in a matrix form. So here, firstly, let's see well-determined linear systems. So here we have two unknown variables and two equations. So by rewriting these equations in a matrix form of Ax is equal to b, we can have the 2 by 2 sized A matrix. And if there's inverse of A exists, then the solution can be simply obtained by multiplying A inverse to a B matrix. So the question is, when the A inverse exists. So you may have a question that if we have two variables and two equations, there could be a chance to having two parallel equations or one exactly overlapped case. So here, or in this case, both case indicates you cannot have the inverse of A. So in this case, you may find there is no solution, or there could be many solutions. So here we assume that the well-determined linear system is just we have only one overlapping point, so we have one exact solution. Yeah, so here let me summarize the three types of systems of linear equations in a matrix form. In the first case, for the well-determined case, we know that the number of variables is equal to the number of equations. So here, by seeing this, we can clearly see that the matrix A has a square form, which means the A can be written as n by n. And in the case of underdetermined case, we know that the number of variable is larger than the number of linearly independent equations. So here we only have one constraint, so it seems like the matrix A seems fat. So here the size of A matrix is equal to 2 by 1, where the number of row is smaller than the number of column. And the final case is overdetermined, where the number of variable is smaller than the number of constraints. So here the matrix A has very skinny form, so it can be like this. So here the size of A matrix is equal to 2 by 3. So we have a more the number of row compared to number of columns. Yeah, and of course, as an engineer, it is ideal to encounter well-determined cases, because in this case, we can simply get a solution by multiplying inverse of A times a B. However, as an engineer, when we deal with a data science, it will be mostly the skinny cases where we have many data that are not exactly a match to one point. But in this case, we need to somehow find some optimal solutions. And of course, there could be a chance to encounter underdetermined case where we also should find some the best or optimal solutions. So from now on, I'm gonna talk about how to find the optimal solution when we encounter underdetermined cases or when we encountered overdetermined cases. Yes, so firstly, we're going to take them to for the underdetermined linear system case. So here we call this the way to find the solution is least norm solution. So here for this underdetermined linear system, we know that the solution could be represented like this single line case. So any points on this line could be the solution. But the question is, what could be the best solution, and what points we should select? So here, the way to solve this problem is adding what additional constraints. So here, one of the easiest way is to find the solution of Ax is equal to b that minimize the norm or the L2 norm. So here, this one is additional. This one can be regarded as additional constraint. So here, the reason of the problem of underdetermined case is that the number of variable is smaller than the number of equations or constraints. So here, by adding one additional constraint, we can find the solution that satisfies these equations. So here by adding this one additional constraint, the problem can be changed to the optimization problem by finding the minimum L2 norm such that the Ax is equal to b. So the optimization problem can be written as like this, and this optimization problem can be interpreted as geometrically like this. So we already know that the solution of Ax is equal to b can be represented like this black solid line. And here, by adding one additional constraint that obtaining the minimum L2 norm, we can find the one solution that has the minimum L2 norm, which makes a right angle of this line to the original Ax is equal to b line. So here, by finding this point, we can find the one solution. So this way is just selecting one solution among many solutions. So without these constraints, any points can be the solution. So among these many solutions, we can have the one solution that is that has the minimum L2 norm. So that's why we call this method as least norm solutions. Then this problem can be solved by this matrix form. Yeah. So in the case of overdetermined linear system, we cannot find the solution that satisfies the whole three equations. So here we cannot find x1 appropriate x1 and x2 that satisfy the three equations at the same time. So there is no solution. But we can somehow find a proper approximated solution of x star that minimize the error between ax and b. So by defining error as equal to ax minus b, this problem finding the x star could be changed to optimization problem finding the minimum L2 norm of this error. So the problem is changed to find x that minimize L1 norm or L2 norm of E. So the remaining problem is that how can you obtain the solution of this optimization problem? The optimization problem can be simply understood by using geometric interpretation. By recalling that the matrix A has the form of this skinny form, this skinny form, we know that the matrix can be rewritten by using the column vector, which is A1 and A2. So here, this is a A1 column vector, and the second law is the A2 column vector. And we know that the product between matrix and vector is just simply is a linear combination, which means the linear combination of these A1 vector and A2 vector. And the linear combination is nothing but the plane that makes A1 vector and A2 vector. By changing the coefficient of this x1 and x2 variable, we can span the whole plane. So this one is the physical meaning of, so this plane is the physical meaning of matrix AX. Then we know that by definition, the error measures the error between ax minus b. So b vector is like this. So error can be any vector that measures the difference between b vector and the plane. And this optimization problem is minimizing L2 norm of this error. So we know that the best solution or optimized solution could be like this by having the right angle between the ax star and the b vector. Yes. And the mathematical representation of the risk norm solution is just simply the projection of b vector onto a subspace U of span of column vector A1 and A2. We know that the column vector A1 and A2 is like this, so the subspace U of span A1 and A2 vector is just simply the dashed plane. And in order to minimize the error L2 norm of E, we know that it should be the orthogonal to this plane. That means we can interpret this B star as the projection of B vector onto this plane. So this is just a geometrical interpretation, and by rewriting it mathematically, we can rewrite this like this. So here, this one is just simply the E vector, which measures the difference between AX star and original B vector. And we know that E vector is normal to this plane. So A and E vector is orthogonal. And we know that in order to satisfy this orthogonality condition, these A plane and E vector should the inner product between the A matrix and the E vector should be 0. So by rewriting this, we can obtain x star is equal to like this. And our ultimate goal is to find the B star, which minimizes the error, and B star is just simply A times X star, which is equal to A times A transpose A inverse and A transpose B. So this is the solution. This is the what we called a least norm solution. Yeah, and that's what we have learned today. Yeah, so let me summarize today's lecture. So today we have learned the basics of linear algebra. So we have reviewed several important concepts. So firstly, we have learned the systems of linear equations. And we have learned how to rewrite systems of linear equations using matrix. And we have learned basics of matrix operations like the product between vectors and product between matrix and vectors. Then we interpret vector and matrix and vector product as a linear matrix transformation, which transforms one vector to another vector. So we have learned several important kinds examples of matrix transformation. And finally, we have looked into several types of systems of linear equations. And there were mainly three types of linear systems. The first one is a well-determined linear systems, so where the number of variables is equal to the number of constraints, so we can exactly define the solution. And the second case is underdetermined linear systems, and here we don't have enough constraints compared to the number of variables. So in order to solve this problem, we have introduced a least norm solution. And the final case is overdetermined linear system, which has a skinny matrix form, and it's usually used. You may encounter these case very often when you deal with the data-driven science. And here, in order to overcome this overdetermined linear systems, we have learned a least square solution by solving the minimum, by finding the solution that has the minimum error. Yeah, that's what we have learned today, and that's it for today's lecture. Yeah, thank you for your listening.